Module 17, Lecture A, Forests, Extra Trees. By the end of this lecture, you will be able to fit random forest and extra trees models for classification and regression, configure bootstrap, feature subsampling, out-of-bag scoring, and parallel training, and interpret impurity-based feature importance while recognizing its limitations. Forest model fitting. Random forest classification. Random forest classification predicts categories by combining the votes of many decision trees. This reduces the risk of overfitting that can occur with a single tree and makes predictions less sensitive to small changes in the data. Because different trees can capture different patterns, the overall model is often more stable and accurate, especially for complex or nonlinear relationships. A random forest classifier starts with labeled data and builds many decision trees. Each tree uses a different sample of the data and considers different features when making splits, which helps the trees make different kinds of errors. The forest then combines their predictions, allowing it to capture complex patterns across variables without requiring predefined interactions. Random forest classification produces both class labels and probabilities, supporting automated decisions and human review. For example, it can flag transactions as legitimate or suspicious, and use probability scores to guide approval or further investigation. Although it works well with noisy and mixed data, it must be tested on separate data, especially when classes are imbalanced. In those cases, evaluation should consider the costs of false positives and false negatives, not accuracy alone. Python code, random forest classification. Train a random forest classifier, then evaluate it by comparing its predictions with the held-out labels. Report the model's accuracy and identify which features were most important to its decisions. We import key tools from Scikit-Learn to build and evaluate a wine classification model. The wine dataset loader provides the data. The random forest classifier creates an ensemble of decision trees for prediction, and the accuracy score measures how well predictions match the true labels. We also use the train test split tool to separate the data into training and testing sets, so performance is evaluated on unseen data. We load Scikit-Learn's built-in wine dataset, which provides measurements and class labels for wine samples. The feature data contains the sample attributes, and the target data contains the matching wine categories, making the dataset ready for a classification task. Before training, confirm that the number of feature rows matches the number of target labels, so every example has a label. If they do not match, raise an error to signal the data mismatch. This simple validation helps protect data integrity and prevents problems during model training and evaluation. We split the dataset into training and testing sets using Scikit-Learn's train test split function. 25% of the data is held out for testing, so the model is evaluated on unseen data. The split is stratified to keep class proportions consistent, and a random state is set to make the result reproducible. We create a random forest classifier in Scikit-Learn using 100 decision trees and a square root feature selection strategy at each split. A fixed random state makes the results reproducible, and all available processors are used for faster training. The model is then fit to the training features and labels, so it can learn patterns and later make predictions on new data. Use the trained random forest model to predict labels for the unseen test data. Then compare those predictions with the true labels to calculate accuracy. This accuracy shows how well the model generalizes to new data. To find the most important feature by impurity in a random forest, identify which feature has the highest importance score. That position points to the corresponding feature name in the wine dataset, and the score itself shows how strongly that feature influences the model's predictions. The output reports the Scikit-Learn version to support compatibility and reproducibility, then shows the model's test accuracy as a clear measure of performance on unseen data. It also identifies the most important feature and its importance score, helping explain which input most influenced the model's predictions. This script trains a random forest classifier on the wine dataset and evaluates it on a stratified test set containing 1/4 of the data. The model uses 100 trees and considers the square root of the feature count when choosing split features. After training, it reports the scikit-learn version, the test accuracy, and the most important feature based on impurity reduction, including that feature's importance score. Random forest regression. Random forest regression predicts numerical values by averaging the results of many decision trees trained on different subsets of data. This makes predictions more stable and less noisy than relying on a single tree. It works especially well for tabular data with complex nonlinear relationships, without requiring a predefined model shape. A random forest regressor predicts a continuous target by building many decision trees from the input features. Each tree splits the data in different ways to find groups with similar target values, so the forest can capture varied patterns. For a new case, the trees each make a prediction, and the model averages them to reduce the effect of any extreme tree. This makes random forests useful for mixed predictors and threshold effects. In random forest regression, aim for both accurate predictions and good performance on new data. More trees can make results more stable, but they require more time and memory, while deeper trees can model complex patterns but may overfit noisy or limited data. Random forests are often a strong baseline because they need little pre-processing and handle many practical problems well, though they may not be ideal when simple explanations or very fast predictions are required. Python code. Random forest regression. Fit a random forest regression model by averaging many decision trees to produce more stable predictions. Then evaluate the model by comparing its predictions with the held-out target values. We import key scikit-learn tools for a regression task using the built-in diabetes dataset. The random forest regressor will build predictions from multiple decision trees, while mean absolute error measures how far predictions are from the true values on average. We also use the train test split function to separate the data into training and testing sets, so the model can be evaluated on data it has not seen before. We load the diabetes dataset from Scikit-Learn as a small example for regression. It separates the data into features, which are the input predictors, and a target, which is the outcome to predict. This structure supports supervised learning, where a model learns to predict the target before training. Confirm that the feature data and target values have the same number of rows. This ensures every example has a matching target, which is required for supervised learning. If the counts differ, raise an error to stop processing inconsistent data. The dataset is split into training and testing sets using Scikit-Learn's train test split function. 25% of the data is reserved for testing, so the model can be evaluated on unseen examples. A random state of 42 makes the split reproducible, keeping experiments consistent. We create a random forest regressor that combines many decision trees to make predictions. The model uses 100 trees with a maximum depth of 5, helping it learn useful patterns while limiting overfitting. A fixed random state makes the results reproducible, and using all CPU cores speeds up training. Finally, the model is fit to the training data, so it can learn from the features and target values before predicting new data. Use the trained random forest model to predict outcomes for the unseen test data. Then compare those predictions with the actual target values. The mean absolute error summarizes the average size of the prediction errors, giving a clear measure of how well the model performs. The output reports the Scikit-Learn version for reproducibility, then shows the model's test mean absolute error as a simple measure of average prediction error. It also displays the first 5 true test values and the first 5 model predictions, rounded for easy comparison. This script trains a random forest regression model on the diabetes dataset. It splits the data into training and test sets, uses 100 trees with limited depth, and makes predictions on the test data. It then reports the mean absolute error and compares the first few true and predicted values to give a quick view of model accuracy. Extra trees fitting. Extra trees are an ensemble method similar to random forests, but they add more randomness by choosing split points randomly when building each tree. This increases diversity among the trees and can reduce variance, which may improve performance on complex data. For classification, the trees vote on the final class, and for regression, their predictions are averaged. An ExtraTreesClassifier builds many decision trees using randomized splits, so different trees learn different patterns in the data. This randomness helps reduce overfitting and works well for complex classification problems with irregular or nonlinear boundaries. By combining many imperfect trees, the model produces more robust and reliable predictions, such as in fraud detection or land cover classification from satellite data. An ExtraTreesRegressor predicts continuous values by building many randomized decision trees and averaging their outputs. It works well for complex regression problems with interacting factors and can be efficient on large datasets. Key settings, such as the number of trees, tree depth, and data quality, affect performance, so the model should always be tested on new data to check that it generalizes well. Python code, extra trees fitting. Fit an extra trees model for classification by combining many randomized decision trees. The trees vote together to make predictions, and the fitted model can be summarized using its accuracy and feature importances. We import key Scikit-Learn tools for a wine classification task: the wine dataset loader, the ExtraTreesClassifier, an accuracy measure, and a train test splitting tool. Together, these let us load the data, train an ensemble of decision trees, and evaluate its performance on unseen test data. We load Scikit-Learn's built-in wine dataset, which includes measurements for different wines and their category labels. The input features are separated from the target labels, preparing the data for later processing and model training. Check that the feature data and target labels have the same number of rows, so each example has a matching label. If they do not match, raise an error, because misaligned data cannot be used reliably for model training or evaluation. The dataset is split into training and testing sets using Scikit-Learn's train test split function, with 25% reserved for testing. Stratifying by the target keeps the class distribution consistent across both sets, and using a fixed random state makes the split reproducible. An ExtraTreesClassifier is created using 100 decision trees to make predictions. It considers the square root of the available features at each split, uses a fixed random state for reproducibility, and runs on all CPU cores to speed up training. The model is then fitted to the training data so it can learn patterns between the features and target labels. The model uses its ensemble of decision trees to predict classes for the test data. Its performance is then measured by comparing those predictions with the true test labels using an accuracy score, showing how well it works on unseen data. To find the most important feature by impurity, identify the largest value in the model's feature importance scores. The position of that value points to the corresponding feature name in the wine dataset. Together, the feature name and its score show which input most strongly influenced the model's predictions. The output reports the Scikit-Learn version for reproducibility, then shows the ExtraTrees model's test accuracy rounded to 3 decimal places. It also identifies the feature with the highest impurity-based importance score. highlighting the input that most influence the model's decisions. This script uses Scikit-Learn's ExtraTreesClassifier to classify the wine dataset. It loads the data, splits it into training and test sets, trains an ensemble of 100 trees, and reports the test accuracy. It also shows which feature contributed most to the model's decisions based on impurity reduction, along with the Scikit-Learn version and that feature's importance score. Randomization settings. Bootstrap sampling. Bootstrap sampling helps random forests build stronger models by training each tree on a different sample of the data, chosen with replacement. This makes the trees vary in what they learn and the errors they make. When their predictions are combined, the result is usually more stable and reliable than a single decision tree. Bootstrap sampling lowers variance by making the trees in an ensemble more diverse. Since a single decision tree can react strongly to small changes in the data, training trees on different sampled mixtures reduces that sensitivity. When their predictions are combined, individual quirks tend to cancel out, producing a more robust model that generalizes better to new data. Bootstrap sampling affects how ensemble models are trained and evaluated. In random forests, each tree usually learns from a resampled dataset, which also enables out-of-bag evaluation using unused observations. Extremely randomized trees may skip bootstrapping and rely more on random split choices. Whether to use bootstrapping depends on the desired tree diversity, need for out-of-bag scoring, dataset size, and computational cost, with validation especially important for smaller datasets. Python code. Bootstrap sampling. In a forest model, each tree is trained on a bootstrap sample, meaning a resampled version of the training data. The rows left out of each sample, called out-of-bag rows, can be used to estimate performance without needing separate validation data. We import key Scikit-Learn tools for a classification workflow: the breast cancer dataset loader, the RandomForestClassifier, and the train test split function. Together, these let us load a built-in dataset, build a model using multiple decision trees, and divide the data into training and testing sets to evaluate performance on unseen data. We load Scikit-Learn's breast cancer dataset, a common example for classification tasks. The dataset includes input features and target labels, which are separated so the model can learn from the features and be evaluated against the correct outcomes. Before training, the code verifies that the feature data and target labels have the same number of rows. This confirms that every feature vector has a matching label. If the counts differ, it raises an error to prevent incorrect model training. The dataset is split into training and testing sets, so the final test score stays independent of model training. Scikit-Learn's train test split function divides the features and target data, with 25% reserved for testing. Stratification keeps the class proportions the same as in the original dataset, and a fixed random state makes the split reproducible. We build a random forest classifier with 100 trees. Bootstrap sampling trains each tree on a random sample with replacement, which also enables out-of-bag scoring to estimate performance. The model uses all available processors for faster computation and a fixed random state for reproducible results. The random forest classifier is trained on the training features and labels using bootstrap sampling. It builds multiple decision trees from different sampled versions of the data, creating an ensemble designed to make more reliable predictions on new, unseen data. We compare two performance measures for the random forest model. The test score shows how accurately the model predicts unseen test data, while the out-of-bag score gives an internal accuracy estimate using samples left out during bootstrap training. Together, these scores provide a concise view of model performance without requiring an extra validation set. We check the Scikit-Learn version to support reproducibility. then confirm that the random forest used bootstrap sampling. We also review the out-of-bag score, which estimates performance from unused bootstrap data, and compare it with the held-out test accuracy. Together, these scores help assess how well the model generalizes to new data. This script shows how bootstrap sampling works in a random forest classifier using the breast cancer dataset. The data is split into training and independent test sets, and the model is trained with 100 trees, bootstrap sampling, and out-of-bag scoring enabled. Each tree learns from a resampled version of the training data, while the unused samples provide an internal estimate of performance. The script then compares the out-of-bag score with the test score to show how well the model generalizes. Feature subsampling. Feature subsampling makes forest-based methods more robust by adding randomness to how trees are built. At each split, the algorithm considers only a random subset of features, so different trees can focus on different patterns in the data. This reduces dependence on a few dominant predictors and creates a more diverse, reliable ensemble. Feature subsampling helps make trees in a forest model less similar to each other. By preventing every tree from always using the strongest predictors, it encourages the model to consider other useful patterns, such as blood pressure or lifestyle, instead of only age in a medical setting. This added variety helps the ensemble generalize better and base predictions on multiple perspectives rather than one repeated pattern. Feature subsampling in forest models balances tree strength with diversity. Using too few features can make trees weak, while using too many can make them too similar and reduce the benefit of the ensemble. Classification forests often use fewer features per split than regression forests, but the best choice depends on the data. Extra trees add more randomness through random split selection, which can lower variance and speed training, though it may slightly increase bias. Python code. Feature subsampling. This example compares feature subsampling settings in a forest model. Using fewer features can make the trees more diverse, but test accuracy reveals the trade-off in performance. We import key Scikit-Learn tools for a breast cancer classification example. The dataset loader provides the built-in breast cancer data. The RandomForestClassifier builds a model using multiple decision trees. The train test split function separates data for training and evaluation, and the accuracy score measures how well the model predicts unseen cases. We load the breast cancer classification dataset from Scikit-Learn, then separate it into input features and target labels. This keeps the data and its correct answers organized for training and evaluating a machine learning model. Before modeling, the code verifies that the feature data and target labels have the same number of rows. This ensures every feature vector has a matching label. If they do not align, it raises an error to prevent problems during training and evaluation. The dataset is split into training and testing sets using Scikit-Learn's train test split function. 30% of the data is kept for testing, while stratification preserves the original class balance for fair evaluation. A fixed random state of 42 makes the split reproducible across runs. We create a random forest classifier with 120 trees, allowing each tree to consider all features when choosing splits. A fixed random seed makes the results reproducible, and using all CPU cores speeds up training. The model is then fitted to the training features and labels so it can learn the patterns in the data. A random forest classifier is trained with 120 decision trees. At each split, each tree considers only the square root of the available features, which helps make the trees more diverse. A fixed random seed makes the results reproducible, and all processors are used to speed up training. The model is then fit to the training data to learn patterns from the features and labels. We compare two models by measuring their accuracy on the test data. One model uses all available features, while the other uses feature subsampling, considering only some features at each split. This shows how subsampling affects performance by making the model more diverse. We collect predictions from each individual tree in two random forests, one using all features and one using feature subsampling. For each forest, every tree predicts on the test data. These individual predictions can then be compared with the overall forest prediction to assess how much the trees agree and how diverse their decisions are. We first use the forest trained on all features to predict the test data, giving its overall model prediction. We then predict the same test data with the forest that uses feature subsampling. These results will be used to compare how often individual trees agree with their forest's overall prediction. The code measures how often individual trees agree with the final prediction of their forest. It does this for both the forest using all features and the forest using feature subsampling by comparing each tree's predictions to the overall forest prediction and averaging the match rates. This gives a simple measure of how consistent the trees are with the forest's final decision. We compare the two forests by calculating each one's average agreement, the total agreement score, divided by the number of trees. This shows how consistently the trees align with the forest's overall prediction. Doing this for both the all features forest and the feature subsampling forest lets us compare how strongly their trees agree. The output reports key details for comparing two random forest models. It shows the Scikit-Learn version, the dataset name, and the number of features, then compares model accuracy using all features versus square root feature subsampling. It also reports the average agreement among trees for each forest, helping assess how much consensus or diversity exists within the models. This script compares two random forest classifiers on the breast cancer dataset to show how feature subsampling affects performance. One model can use all features at each split, while the other uses only the square root of the feature count. The full feature model may score higher on accuracy, but the subsampled model often has lower agreement among its trees, showing greater diversity. This illustrates the trade-off between accuracy and robustness, since more diverse trees can help reduce overfitting. Out-of-bag scoring. Out-of-bag scoring estimates how well a bagged model, such as a random forest, will perform on new data without using a separate validation set. Because each tree is trained on a bootstrap sample, some observations are left out and can act as test cases for that tree. The model combines predictions from trees that did not train on each observation and compares them with the true values to produce an internal validation score. Out-of-bag scoring estimates model performance without setting aside a separate validation set, making it useful when data is limited. Each record can help train some trees while testing others, which preserves more data for fitting. It also gives quick feedback during model development, helping tune choices such as the number of trees or feature subsampling. Out-of-bag scoring is a useful quick check for bagged forests, but it must be interpreted carefully. It only works when bootstrap sampling is used, and it is still just an estimate, not a substitute for an independent test set. The score can be too optimistic or unstable with small, related, or time-based data, so use it as a diagnostic while still planning proper validation when needed. Python code out-of-bag scoring. Out-of-bag scoring in random forests uses the observations left out of each bootstrap sample as built-in validation data. This provides an internal estimate of model accuracy without needing a separate validation set. Comparing out-of-bag accuracy with test accuracy helps check whether the model's internal performance estimate matches its performance on unseen data. We import key Scikit-Learn tools for a classification workflow: the breast cancer dataset loader, a RandomForestClassifier, an accuracy measure, and a train test splitting tool. Together, these let us load the data, train a model made of multiple decision trees, split the data into training and testing sets, and evaluate how well the model performs on unseen examples. We load Scikit-Learn's breast cancer dataset, a common example for classification tasks. The dataset is separated into input features and target labels, which lets a machine learning model learn from the data and compare its predictions with the expected outputs. The code first checks that the feature data and target labels have the same number of entries, so each feature row has a matching label. If they do not match, it raises an error. This prevents misaligned data from causing incorrect model training or evaluation. The dataset is split into training and testing sets using the train-test-split function. 25% of the data is kept for testing, while stratification preserves the same class balance in both sets. A fixed random state makes the split reproducible across runs. A random forest classifier is configured with 200 trees and bootstrap sampling, so each tree trains on a random sample of the data. Out-of-bag scoring uses the unused samples from each bootstrap to estimate performance internally. The model also uses all CPU cores for faster training, and a fixed random state to make results reproducible. The random forest model is trained on the training data, learning patterns from the input features and labels. During training, it also calculates an out-of-bag score, which estimates performance using samples left out of each bootstrap sample. This provides a built-in validation measure without needing a separate validation set. To compare internal validation with a held-out test set, use the random forest to predict the test labels, then measure accuracy against the true labels. This test accuracy shows how well the model performs on unseen data and provides a benchmark for the out-of-bag accuracy. We report the Scikit-Learn version and the number of training rows to support reproducibility and show the training data size. Then we compare the random forest's out-of-bag accuracy with its held-out test accuracy to assess performance using both internal validation and a separate test set. The out-of-bag score is available only because bootstrap sampling is enabled. This example shows how out-of-bag scoring can validate a random forest classifier on the breast cancer dataset. The data is split into training and test sets, and the model is trained with bootstrap sampling, so it can estimate accuracy using samples left out of each tree's training data. After training, the script compares this out-of-bag accuracy with the test accuracy. Because these values are usually close, out-of-bag scoring provides a useful internal estimate of performance without needing a separate validation set. Forest Importance Inspection. Parallel forest building. Parallel forest building makes random forests and extremely randomized trees efficient, because each tree can be trained independently on separate processor cores. This lets many trees learn patterns at the same time, then combine their predictions into one final model. As a result, training is much faster, especially for large datasets or complex feature spaces. Parallel training speeds up impurity-based feature importance by combining importance values from many trees more efficiently. Each tree measures how much features reduce impurity during splits, and features that often create strong splits receive higher scores. In a hospital readmission model, variables such as prior admissions or age may rank highly if they help form more homogeneous groups. However, parallelism only improves speed. The scores are still not causal or necessarily unbiased, and they depend on how the forest is built. Parallel forest building speeds up training and makes it easier to test more trees, compare models, and check whether feature importance stays consistent across runs. This is especially important in high-stakes settings like credit risk or equipment failure prediction. However, parallelism does not remove bias in importance scores, so results should still be validated and questioned carefully. Python code, parallel forest building. This example compares settings for training a random forest in parallel. Feature importance is combined across many trees, and faster fitting does not remove the usual limits on how those important scores should be interpreted. We import key Python tools for a machine learning workflow: NumPy for numerical array operations, Matplotlib for visualizing results, and Scikit-Learn for modeling. From Scikit-Learn, we use a classification data generator to create a synthetic dataset, a RandomForestClassifier to build an ensemble model, and a train test splitting tool to evaluate performance on separate data. We create a synthetic classification dataset with Scikit-Learn to study model behavior in a controlled setting. It contains 1,200 samples and 8 features, including 3 informative features and 1 redundant feature. A fixed random state of 42 makes the results reproducible. Create a set of feature names, 1 for each of the 8 dataset features, so later feature importance scores are easier to interpret. Then verify that the dataset has the same number of features as the names provided. If the counts do not match, raise an error to prevent misleading interpretation and make debugging easier. We split the dataset into training and testing sets using Scikit-Learn's train test split function. 25% of the data is kept for testing, and stratification preserves the class balance in both sets. A fixed random state makes the split reproducible in future runs. We configure a random forest classifier with 200 trees. At each split, it considers the square root of the total features, a common choice for classification. The model uses all available CPU cores to speed up training, and a fixed random state makes the results reproducible. Train the random forest on the training data, so its decision trees can learn patterns between the features and the target. Then measure its accuracy on the test data to see how well it predicts new cases. Finally, review the feature importances to identify which inputs most strongly influence the model's predictions. To identify the most important features, sort the feature importance scores from highest to lowest. Then, select the top 5 feature names and their matching scores. This highlights which features have the strongest influence on the model's predictions. The code reports the Scikit-Learn version to support compatibility and reproducibility, then shows the random forest model's test accuracy rounded to 3 decimals. It also summarizes the most important features using impurity reduction scores from the model. Each top feature is printed with its importance score, giving a quick view of which inputs most influence the predictions. This code creates a bar chart in Matplotlib to show the most important features and their impurity-based importance scores. It sets up a figure, plots the feature names on the x-axis and their scores on the y-axis, and uses clear labels and a title to explain the chart. Finally, it displays the plot so the feature importances can be visually compared. This script shows how to train a random forest classifier more efficiently using parallel processing. It creates a synthetic classification dataset, splits it into training and test sets, and trains a 200-tree forest using all available CPU cores. Afterward, it reports test accuracy and identifies the most important features, with a bar chart to show which inputs most influence the model's decisions. Impurity importance. Impurity-based feature importance shows which inputs a forest model relies on most by measuring how much each feature improves tree splits. In classification, this means making classes less mixed, and in regression, it means reducing variation in the target values. Features that repeatedly create purer nodes across many trees receive higher importance, giving a quick view of the model's main drivers. Impurity-based feature importance is a fast, built-in way to see which features a forest model relied on most, making it useful for initial model inspection and communication. However, it does not show causality or prove that changing a feature will change the outcome. A feature may appear important because it predicts well, stands in for another factor, or is correlated with other variables. Impurity-based feature importance can be misleading because it often favors features with many possible splits, such as continuous variables or categorical variables with many categories. Correlated features can also divide importance between them, making each one seem less influential on its own. For this reason, impurity importance should be treated as an initial guide and checked against other methods, especially in high-stakes areas like healthcare or finance. Python code, impurity importance. Wait for the next section. This example examines impurity-based feature importance in a forest model. After training, features are ranked by their apparent importance, but correlated features may split that importance between them. We import key Python libraries for a regression workflow: NumPy for numerical arrays, Matplotlib for visualization, and Scikit-Learn for machine learning. From Scikit-Learn, we use tools to create a synthetic regression dataset, build a random forest regression model, split the data into training and testing sets, and evaluate performance with the R-squared score. We create a synthetic regression dataset with 800 samples and 5 features using Scikit-Learn's regression data generator. Only 2 features directly affect the target, and added noise makes the data more realistic. A fixed random state ensures the results can be reproduced, giving a controlled setup for testing whether a model can identify the important features. A new feature is created by slightly modifying the first informative feature with a small contribution from the second, making it correlated with the original data. This correlated feature is then added as an extra column and given a name indicating it is a copy of the first feature. This setup helps examine how the model assigns importance when features are correlated. The code verifies that the feature matrix has the same number of columns as there are feature names. This ensures every data column is properly labeled for later interpretation. If the counts do not match, it raises an error to prevent inconsistent data from causing problems during training or analysis. We split the dataset into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is kept for testing, and a fixed random state ensures the split can be reproduced. This lets us evaluate how well the model performs on unseen data. A random forest regressor is created to model a regression problem using an ensemble of decision trees. It uses 120 trees, limits each tree to a depth of 6 to reduce overfitting, and sets a fixed random seed for reproducible results. The model is also configured to use all available processors for faster training. It is then fitted to the training data so it can learn patterns between the input features and target values for future predictions. After training the random forest model, we use its feature importances to see which inputs most influence its predictions. These scores show how much each feature helps reduce impurity in the model. By sorting the scores from highest to lowest and aligning them with the feature names, we can quickly identify the most important features. The model is evaluated by comparing its random forest predictions with the test targets using the R-squared score, which summarizes how well the predictions fit the actual values. The Scikit-Learn version is printed to support reproducibility, and the score is reported rounded to 3 decimals. The most important feature by impurity importance is also shown with its rounded value, while noting that correlated features may split importance between them. This code creates a Matplotlib bar chart to show sorted feature importances from a random forest model. It sets up the figure, draws steel blue bars whose heights represent mean impurity decrease, and labels the title and axes to explain the plot. The feature names are angled for readability. Then the layout is tightened and the chart is displayed. This script shows how a random forest regressor estimates feature importance in a regression task. It creates synthetic data with a few informative features, adds a correlated feature, trains and tests the model, and reports its R-squared performance. It then ranks features by impurity-based importance and visualizes the results, showing that correlated predictors can split importance between them. Missing monotonic constraints. When interpreting feature importance in random forests or extra trees, remember that these models do not enforce monotonic relationships. A feature may strongly affect predictions, but the model might use it in a direction that conflicts with domain expectations. For example, in lending, a higher debt-to-income ratio should not make a borrower appear less risky when everything else is unchanged. So feature importance shows influence, not whether that influence is directionally sensible. Impurity-based feature importance in forest models shows how much a feature helps reduce uncertainty, but it does not show whether the learned effect is stable or sensible. A feature can appear important because it creates useful splits, even when those splits imply unexpected patterns, such as larger homes being predicted as cheaper or medical risk decreasing with age in some regions. Extra trees can make this harder to detect because their random split thresholds may improve generalization while also producing irregular behavior. So important scores should be interpreted alongside checks of the model's actual relationships. When monotonic behavior matters, feature importance alone is not enough. Analysts should also check how predictions change as key features vary within realistic ranges, using tools such as partial dependence or individual conditional expectation plots, while being cautious with correlated features. In high-stakes settings like credit scoring or healthcare, models that violate expected directional rules can reduce trust and make decisions harder to justify. If those rules are required, use models with monotonic constraints or verify compliance after training. Python code. Missing monotonic constraints. Forest importance scores may not show whether a model behaves in the expected direction. This example uses a visual check for monotonic patterns and shows that local predictions can still reverse. We import key Python libraries for numerical work, visualization, and machine learning. NumPy supports array operations and math functions. Matplotlib's plotting tools create visualizations. And Scikit-Learn provides the RandomForestRegressor for regression using many decision trees. The full Scikit-Learn library is also imported to access version information and related utilities. We create synthetic data that generally increases by generating 220 evenly spaced debt-to-income ratio values from 0 to 1. A fixed random seed makes the results reproducible, and normally distributed noise with mean 0 and standard deviation 0.08 adds realistic variation. This produces data that follows an upward trend without being perfectly linear. The risk values are made more realistic by combining the debt ratio with a small wave-like variation and random noise, creating natural fluctuations in the data. The debt ratio is then reshaped into a single-column, two-dimensional format, so it can be used by machine learning models. The code validates the input data before running single-feature regression. It checks that the feature and target data have matching numbers of entries, and that the feature data contains only one column. If either check fails, it raises an error because the data is not in the expected format. A random forest regression model is built to predict risk score from debt-to-income ratio. It uses 120 trees, a fixed random seed for reproducible results, and a minimum of 3 samples per leaf to reduce overfitting. After training on the data, the model can learn flexible patterns without requiring the relationship to be strictly increasing or decreasing. We create a set of evenly spaced debt-to-income values from 0 to 1 and format them for the model. The trained random forest then predicts a risk score for each value, showing how predicted risk changes across the full debt-to-income range. The code checks whether predicted risk ever drops as the debt ratio increases by comparing consecutive predictions and counting meaningful decreases. It then records how many such reversals occur. Finally, it extracts the debt ratio's importance score from the trained random forest model, showing how strongly the model uses that feature in its predictions. The code reports the Scikit-Learn version to provide context for compatibility, then shows the debt ratio feature's impurity importance rounded for readability. It also counts local monotonicity violations, meaning cases where predictions decrease even though they are expected to increase as the debt ratio rises. Together, these outputs help assess both the feature's influence and whether the model follows the expected monotonic pattern. Create a plot to compare the original debt-to-income ratios with risk scores and the random forest model's predicted risk across a range of debt ratios. The training data is shown as small, transparent points, while the model prediction is shown as a clear, crimson line. The goal is to visually check whether the predictions change direction, showing that high feature importance does not necessarily mean the model behaves monotonically. This script shows that a random forest regressor can give predictions that violate an expected monotonic trend. Using synthetic data where risk generally rises as debt-to-income ratio increases, the model predicts risk across a range of debt levels and checks for places where higher debt leads to lower predicted risk. It reports the number of these reversals and the feature importance score, then visualizes the issue. The key lesson is that high feature importance does not guarantee consistent directional behavior in a model's predictions. In this lecture, you learned to fit random forest and ExtraTrees models for classification and regression, configure bootstrap, feature subsampling, out-of-bag scoring, and parallel training, and interpret impurity-based feature importance while recognizing its limitations. In the next lecture, Lecture B, we will go over bagging embeddings.
Thank you for your attention. See you all in the next lecture.